My name is Saini and I am Assistant Professor in Akgec Engineering College. Today the topic of discussion is lattices. Now, what is a lattice? First of all, if you want to study about the lattice, you should know about what is a poset. A poset is a set which satisfies the properties of reflexive, antisymmetric, and transitive. Then it is called a poset. And what is a lattice now? A lattice is a partial ordered set. It is also called poset, in which for every pair of elements A and B, if we take any two elements from a poset, then it have the greatest lower bound and the least upper bound for both those elements, right? Now, if we are talking about any two elements A and B of that poset, we should have a greatest lower bound of that two elements and least upper bound of those elements. Greatest lower bound is given by this AND symbol and the least upper bound is shown by the OR symbol. Let A be a subset of a poset S with some operation if U is an element of S such that A is related to U. For all elements A belonging to A, then U is called the upper bound of A. Similarly, if I is an element of S such that I is related to A, for all elements of A, then I is called the lower bound of A. Now, let's see this diagram, right? This is a poset, we all know. Let us consider two elements, 2 and 6, right? Now, all the elements which are related to 2 and 6 on the upper side will call the upper bound, and all the elements that are related to these on the lower side are called the lower bounds. But the condition is that it should be related to both the elements. Relation means there should be a direct or indirect path between those elements, right? If we can say that 2 and 6, if we see the upper bounds now, all the upper bounds, like if the upper numbers are 8, 4 and 12, right? And 6 also, right? Because 6 is higher to 2, so it will come in the higher boundaries. So there are 4 elements, 6, 4, 8 and 12 on the upper side. Now, all are not upper bounds, but we have to see which are related to both, right? Now, 2 to 4, it is a path, but 6 to 4, there is no path, right? We are not to come backwards, we have to just go upwards. So, 2 to 4, there is a path, and from 6 there is no path to 4, so 4 is not the upper bound. From 2 there is a path to 8 and from 6 there is no path to 8. We cannot come down, we have to go upsides only. So there is no path to 8, so 8 is also not the upper bound. Now to 12. Now let's consider 12. From 2 there is a path, from 6 also there is a path. So we can say that 12 is one of the upper bounds of both the elements. Now from 2 there is a path to 6 and 6 is related to 6. There is always a path between the same element as the reflexive property is there. So in that case for 2 and 6, 6 and 12 are the upper bounds of these two elements, 2 and 6. Now for lower bounds also we have to see the same thing. Now we have to check only downwards. Now we will not go in any other direction. From now the contenders for the lower bounds are 2, 1 and 3, right? Now let's consider 3. From 3 there is a path between 6 and 3, but there is no path between 2 and 3. So 3 will not be the lower bound. From 1, 2 there is a path, 6 also there is a path, right? So 1 can be the contender and 2 is there. There is a path from 6 to 2. So 1 and 2 will be the lower bounds of this 2 and 6. Now we were talking about GLB and LUB, right? Greatest lower bound. Greatest lower bound means this one, which is the nearest to that numbers, two numbers. Nearest to these numbers from the downside means from the down, which is the greatest, is the greatest lower bound. So from, if we can see this diagram, 2 and 6, 2 is the nearest to them, so 2 will be the greatest lower bound in this case. And if we say the upper bound, the nearest one is 6. 6 and 12 are the contenders, but the 6 is nearest one, so 6 will be the least upper bound. This is the way to find out the upper bounds. Now, the properties of lattices. Idempotent law, A join, this is called join A. A join A means when an element is operated with itself and we have to find out the least upper bound of this, then it is the element itself, and the greatest lower bound also is the element itself. Commutative law, if A join B is equal to B join A, and A meet B is always equal to B meet A. Whatever is the element, if the elements are like this, A and B, if we are to find out the join of this, A and B will be similar to B and A. There is no change in that. This is called the commutative property. Associative law, A join B join C is equal to A, if A join B and B with join C. Similar is the case with the meet. Absorption law, A join A meet B is equal to A meet A join B is equal to A. Distributive law, again, if there is a different operation, different elements are there, then the first element will be distributed over the both. Now let us check D36 is a lattice or not, right? First we will take out the elements. All the divisors of 36 will be here to draw D36. Now first of all, the first step in this is we will draw a hash diagram of this D36. The lowest element is 1, 1 is related to 3, 1 is related to 2. But 3 and 2 are not related to each other because they do not divide each other. 3 and 2 are related to 6. 3 is related to 9, 9 is related to 18. 2 is related to 4, right? And this 6 is related to 18, 6 is related to 12, and 6 is related to 36 also. 6 is related to 36. 12 is related to 18. Between every two elements that are related, there should be a path, direct or indirect path. So we are getting this from this. Now we have to find out whether it is a lattice or not. This we know that it is a poset, but it is lattice or not, we have to check the greatest lower bound and least upper bound of all the two elements in this, right? Now first we will make a meet table. Meet table means least upper bound we have to check about this. Now we will take the elements on the column 1, 2, 3, 4, 6, 9, 12, 18 and 36. These are all the vertices of this, and here also we will take the same. Now we will pick the first element. According to the property, when we take a meet of an element with itself, then we get the element itself. 1 and 2. 1 and 1 we will get 1, okay. Now 2 and 1. 2 and 1, right? Now 2 and 1, at the lower side we have to see which one is the nearest one. So on the lower side 1 is nearest, so we have taken 1 here. Similarly with 3 and 1, 1 is lower, we have taken 1 here. Similarly with 4 and 1, 4 and 1, right? This is the relation, and the lower bound is 1, right? So 1 we have calculated this. Similarly for 6, 9, 12, 18, 36, everyone, the lowest element is 1, so always the 1 will come here only, and it is the nearest one. Now let's check about the second column, 2 and 1. 2 and 1. 1 and 2 will be, if 1 and 2 and 1 is 1, right? 2 and 1 or 1 and 2 will have the same, according to the property, commutative property will have the same meat. So it will be 1. Now 2 and 2 will have 2 according to the absorption property, right? And 3 and 2. Now you check about 3 and 2. 3 and 2 both are first intersecting at 1. So the answer will be 1. 4 and 2. 4 and 2. Right? The first intersection will be downwards. Now the contenders are 2 and 1 also. Right? But 1 is far away, 2 is nearest. So 2 will come in the least upper bound. 6 and 2. Now 6 and 2. Now we will see this is the relation in between. The lower one will come. So 2 will be here. 2 and 9. 2 and 9. 2 and 9 are first intersecting at 1. So 1 will come here. 2 and 12. 2 and 12. There is a path in this. So when there is a path in that, nothing you have to not to worry about, just put the lower element in that. So 2 will be there. And 2 and 18, again there is a path, so 2 is lowest. 2 and 36, again there is a path, and the 2 will be the lowest. You can see here 2 and 18, right? There is a path in this, right? So the lower element will be the least upper bound. Now let's come to the third column, right? 3 and 1. 3 and 1. Again there is a path and 1 is lowest, so it will come. 3 and 2. 3 and 2, we have to check where they are intersecting at 1. Again 1. Similarly, for all the elements, we will make this table and we are able to find out the meet between each and every two elements. Each and every pair we are getting one least upper bound, right? Now let's go for the join now. Join means the greatest lower bound, right? This is the least upper bound. Now here we have to see the upper side. 1 and 1. 1 and 1. Again 1. 2 and 1. 2 and 1. Now this here, when we are seeing the join, we have to see the upper element, right? Upper nearest element. So this is the 2. 2 is nearest, we will write here 2. 3 and 1. 3 and 1, upper element 3. 3. Similarly, we can make this whole column. Now let's go to the second column. 2 and 1 again will be the same 2. 2 and 2, 2. 2 and 3. 2 and 3. Now we have to go to the upper side, right? There is no relation between them. So where they are intersecting on the upper side, that is 6. So 6 is the answer. 4 and 2. 4 and 2, there is a relation, so upper element will be there. 6 and 2, there is a relation, 6 will be there. 9 and 2. 9 and 2, there are no relations. So we will check the intersection. It will come at 1. So sorry, at the upper side we have to see, no? So upper side we can see that they are intersecting at 18. Then 18 will be the answer. 12 and 2, there is a relation, right? So upper wall will be the, so 12 and 2, there is a relation there, and upper one is 12, so 12 will be the bound there, right? Similarly 18, similarly 36. So this way we can make out the table, and here we can see that we are able to find the join for each and every pair of elements in the poset. So it is a lattice. Now let's check this figure, if it is a lattice or not. Let's draw the meet table. Meet table means we have to see the lowest part, which is the nearest part. Now let's write all the elements 1, 2, 3, 5, 6, 10, 15, and 30. All are there. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So similarly, we will write on this side. Right? So we are not requiring this row and this column. Now let's check. 1 and 1 will always be 1. 1 and 2, which is lower, 1. 3 and 1, 1. 5 and 1, 1. 1, 1, 1, 1. Because we all know that 1 is the lower part, so 1 always will be the meet between them. Now 1 and 2. Again 1, 2 and 2, 2. 2 and 3. 2 and 3 are intersecting at 1. Then 2 and 5. 2 and 5 are intersecting at 1. 6 and 2. 6 and 2, there is a relation, so lower element we will take. 10 and 2. 10 and 2, there is a relation. So we will take the lower element. 2 and 15. 2 and 15, again, they are intersecting at 1. 2 and 30. 2 and 30, they are intersect. Again, there is a path in this. The lower element will be there, right? 3 and 1. 3 and 1, 1 relation. 3 and 2. 3 and 2, 1. 3 and 3, 3. 3 and 5. 3 and 5, they are intersecting at 1. 6 and 3. 6 and 3, there is a path, so lower element. 3 and 10. 3 and 10, they are intersecting at 1. And 3 and 15, so 3 will be there. 3 and 15, the nearest one will be 3, right? Then 30 and 3, 30 and 3 will be 3 only, right? Similarly, we can create this table for 5 and 1, 1, 5 and 2, 1 again, 5 and 3, 1 again, 5 and 5, 5, 5, 1, then 5, then 5, and then 5, right? Always take the lower element when there is a path. 6 and 1, 1, then the lower element 2, 3, 1, 6, 1, 1, and 6, right? For 10 and 1, similarly, for 10 and 1, you can take 1. For 2 and 10, 2, 2, 1, 5, 1, 10, 1, and 10, right? 15 and 1, 1, 15 and 2, 1 again, 15 and 3, 3, 15 and 5, 5, 15 and 6, 1, 15 and 6 is 3, sorry, right? 15 and 6 is 3, 15 and 10. 15 and 10 is 5. 15 and 10 is 5. And 15 and 15 is 15. 15 and 30. 15 and 30. 15 is 15. Similarly, you can check if we have made here the right answers. 10 and 5, 5. 10 and 5. Similarly, you can make it for 30, 30 and 1, 1, 30 and 2. 30 and 2 are intersecting at 2, right? 30 and 3. 30 and 3. This is 30 and this is 3, and we can see that they are all intersecting at 3, 30 and 5, right? 30 and 6, 30 and 10, 30 and 15, 30 and 30, 30. Now we are able to find that there is a meet in every two elements. Similarly, we can find out join. Join, we have to see the upper part, 5, 6, 10, 15, 30. 1, 2, 3, 5, 6, 10, 15 and 30. Right? Now, upper side 1 and 1, 1 and 2. 2, 3, 5, 6, 10, 15 and 30. Right? 1 and 2, 2, 2 and 2, 2, 2 and 3, upper side, 2 and 3. See here, 2 and 3, it is joining 6, 5 and 2, 5 and 2, it is joining 10, 6 and 2, it is 6, it is 10, 15, 15 and 2, it is 30, 30 and 30, 30, right? Now 3, 3 and 1, 3, 3 and 2, 3 and 2, it is 6, 3 and 3, it is 3, 3 and 5, it is 15, 3 and 6, it is 6, 3 and 10, it is 30, 3 and 15, it is 15, 30, right? This way you can create the whole table. We will able to find out that there is a join in every of the element, and we can say that it is a lattice. Let's do one more. 5, 5 and 2, it is 10, 5 and 3, 15, 5 and 5, 5, 6, 5, 30, 10, 15, again 30, right? 6 and 1, 6, 6, 6, 30, 6, 30, 30, 30, right? 10, 10, 3 and 10, 30, 10 and 10, 10, 15 and 10, 30, right? And 30 and 30 is 30. 15 and 2 is 30, 15 and 3, 15, 15 and 5, 15 and 5, 15, 15 and 6, 15 and 6, 30, 15 and 10, 30, 15, 30, 30, all will be 30 here. So here we are able to find out that there is a join in everywhere. So it is a lattice. Thank you very much.